right, we are right back at it with part two here. We'll be diving a little bit deeper into volcanism, volcanic eruptions, and magmatic activity in general. Just as a quick recap from part one, again, an intrusive body or magmatic body is when we have magma that has reached a certain temperature and depth at which it can now solidify and cool, where it has sufficient enough time to grow and create bonds and crystallize, forming individual crystals that we can actually see. This can be with fine to medium grained or even large grained, depending on the magma composition and depth or temperature. If they are very large grain, we call it a pegmatic deposit. And intrusive rocks are exposed anytime that it is either uplifted or the overlying sediment or other rock is eroded and carried away. Within intrusive bodies, there are a few different kinds that we can consider. Those are largely categorized as sills, dikes, and batholiths. The easy way to remember a sill is when we have any magmatic intrusion that has spilled out and is sitting atop a underlying bedrock in a horizontal fashion. I like to think of this as it's sort of being spilled out onto a windowsill, hence sill. Then dike is sort of the opposite situation where we have it going straight through. And in this case, we have a dike leading into a sill, but a dike alone is just that vertical portion that cuts perpendicularly through the bedrock. It's not always perfectly perpendicular, but the idea is that the dike is the vertical version of the horizontal sill. And then lastly, we can have a batholith. There are a lot of kinds of liths in general, which is why in this diagram we have a laccolith listed and xenoliths. But here the batholith is just a large magmatic body. I like to think of this and remember it as picturing a bathtub of magma that was just spilled out and dumped in the subsurface. And these different prefixes to lith meaning lithology or rock is the meaning of that. And then all these prefixes denoting just different sizes. So we have batholith, which is the large, laccolith, which is the medium, and xenoliths, which are the small. And here are a couple examples of where we can actually see sills within an exposed bedrock. So notice how all of these planes or these bedrocks are horizontal. You can see the stripes sort of heading in this direction. And we transition from different colors, those are different rock layers, until we get all the way to this area here where it stands out bold and there's no vegetation growing on it, and that's because this part is a little bit more resistant to weathering. It just has a bit stronger bonding, a bit higher hardness than all of these other rocks. These are loosely sedimentary, while this here is igneous because a sill is an igneous intrusive body. So what happens is that while we can't see it in the picture, perhaps a little bit here, it would have come up from below and then spilled out over the existing bedrock and spread out in a horizontal fashion. Same case over here, another sill, different place, but same mechanism, same result. And these can be very easily identified at a distance as well. Dikes, on the other hand, can sometimes be a bit harder to see and to confidently identify. We have both dikes and veins, which veins are sometimes just smaller dikes, but they loosely appear in that vertical sense, but we can have it cross-cutting any which way. As you can see in this picture, we've got some heading in complete opposite directions, but these are all still dikes. In the right-hand example, we have an example of a dike that the surrounding rock and sediment has since been eroded away, again because in this case the rock that was within the dike was more resistant to breakage than whatever was surrounding it previously. So we have this dike now peeking out of the subsurface with a couple of side branches coming off of it. So all of these peaks are actually pieces of that dike, or the main dike with attached veins, or smaller dikes. Here you can see a clear depiction of what was once the overlying rock and bedrock atop what was once the subsurface. So here we have an intrusive igneous body. In this case, it's the dike because it's cross-cutting those bedrock planes nearly perpendicular in a vertical fashion. And over here we have the volcanic neck, which is really the main chamber where the magma from below would enter the volcano before it actually erupts out. So this again has preferentially weathered, or is more resistant to breakage than everything around it. So this is what we end up left with, where you can see that this is that exact volcanic neck here, and here's the dike that we are actually left with in one of our national parks. There are two main types of volcanoes. Number one, shield volcanoes, and number two, composite volcanoes. We can also throw stratovolcanoes in with composite volcanoes. They're one and the same, mainly the difference is their composition, but structurally they're very similar. So a shield volcano is going to be something that has a much slower and calmer flow of lava coming out of it, so they end up being a lot smoother and flatter and wider. Here's one example of a shield volcano. You can see another one here where we've got these long, slow layers. You can see by these sort of movements through it that it's a bit slow. Everything's just spilling out over the top. There's no like violence in this eruption. So there we have this long and wide gradual profile. Opposite of that is the composite volcano, which is going to have a much more violent eruption, usually involving ash coming out of the top, associated with also the lava itself, with a bit more chunky or jagged lava chunks and liquid lava coming out. This ends up giving us a much steeper gradient and a mixture of layers between actual solidified lava itself and thick ash deposits as they fall down. Here's another example of that where you can see it has a much steeper gradient and it's not nearly as smooth as the shield volcano itself. Here are just some scaled examples of some volcanoes that you might be familiar with or you may not be familiar with. It's kind of some national park fun trivia. But this is really to show you the difference between the stratovolcanoes or the composite volcanoes to the shield volcanoes. So Mount Rainier here is a composite volcano, and you can see how small this is, specifically in width in comparison with the shield volcano that it is mapped out on. Here we have the composite cone of Mount Rainier. So we're taking this volcano, blowing it up here, and then we have Sunset Crater, which is just a smaller, having had violently erupted composite volcano. So these are two different composite volcanoes where we can have a range of sizes, but generally the idea is that the shield volcanoes are much wider than the composite or stratovolcanoes. And the main determining factor of whether an eruption will be violent, highly violent, or not very violent at all is the viscosity. And the viscosity describes the amount of dissolved volatiles or gases. Most of the time these gases are dissolved water or steam. And the more viscous the lava, the more violent the eruption will be. So the stratovolcanoes and composite volcanoes have a much more violent eruption than the shield volcanoes. And that's because they have a much higher viscosity in their magma or lava. And what this diagram on the right here is really depicting is that when we have these volatiles or bubbles of gases trapped at depth, they have quite a bit more pressure on them than when they are moving up the volcanic channel And as they come towards the surface, they're having less and less pressure, which means that they will expand because they now have more room to work with. And as those expand and they eject from the volcano, that's what's going to build that violence. It's sort of like shaking up a pop can. These violence levels also correlate to the composition of the magma itself. So if you'll recall, the felsic lavas, which produce the lighter coloration rocks and contain the lighter elements themselves, will produce the more violent eruptions than the alternative mafic lavas, producing darker colored rocks and heavier rocks. And a good way to think about that, remember that, is that the lighter the elements or the lighter the lava itself, the easier it is to throw with the same amount of force. So the heavier lavas will move slower than the lighter lavas. When we have a nice, soft, slow-moving, pillowy-looking lava, we call it pahoehoe, and this is a Hawaiian term, is where this was coined. I have a picture of that here on the left, and if you guys have ever seen videos of people in those bright aluminum-looking suits getting close to lava and maybe scooping up a chunk of it, or taking the temperature, maybe you've seen a picture of that in Nat Geo or a video of it on the History Channel or something like that. That's going to be the pahoehoe lava, those slow-moving, not as threatening lava flows, and those are going to be our mafic rocks that are produced from that. Alternatively, we can have aa lava, and a good way of remembering that is that if you were to step on it, you would, even if it's cooled and solidified, it would be jagged, and you would say ah. So aa is a high viscosity basaltic lava. Also, this term was coined in Hawaii as well. And it is jagged and sharp when it's cooled, and that's because it comes from violent eruptions as pictured on the right. So it's a bunch of chunks of lava flying through the air, and as it cools, it solidifies into that shape. It's not a soft, smooth, pillowy surface. And they move really quite fast as well, which makes them a high threat level to anybody surrounding these volcanoes when they erupt. So once again, as those bubbles nucleate or form out of the magma itself within the deeper part of the chamber, they will begin to rise, and as they get funneled through the volcanic neck or the volcanic channel, that they will experience that pressure change as they move closer and closer to the surface and expand, and that expansion of those bubbles is what increases the viscosity and increases the violence of the eruption. With these violent eruptions, there is a range of byproducts that can occur. We talked a little bit about volcanic ash earlier. Generally, this is much lighter than everything else that is coming out of the volcano and will get picked up by the wind and into the lower atmosphere, creating a stratospheric haze. And these hazes can stretch for several miles and can stick around for several days until the ash finally settles out when we have lower winds or rain, and it falls on top of anything lying below it, such as this picture of volcanic ash on a plant here. We can also have falling lapilli, also referred to as volcanic bombs. These are just molten hunks of lava falling through the air, and they solidify shortly before they hit the ground. We end up with things shaped like this. These are incredibly damaging and can travel some distance. We can also have a collapsing column. Sometimes if an eruption is violent enough and there's enough lava coming out of the top, it will damage the top of the volcano, collapsing that upper part of the volcano, or what we call the column, and it'll fall into itself in part, but also fall out of the sides. And then we can have from that process a mixture of that and the ash that's not lifted into the atmosphere, the ash that falls down, slightly bigger particles with that. We can get nuae ardente, which are these large rolling ground clouds of ash and other volcanic debris. Aside from these products, there are several other hazards associated with violent volcanic eruptions. one of those being poisonous gases, the main constituent being carbon monoxide. You guys probably have carbon monoxide detectors in your home, or at least you should. This is a gas that does not have a smell, but is highly lethal to people and animals. It is also very commonly associated with volcanic eruptions, as it's released in volatile form from those lavas. Another term for the nube ardente that we talked about on the last slide is a pyroclastic flow. Again, these are these rolling ground covering heaps, clouds, if you will, of ash and other volcanic debris that as it comes down the flank of the volcano, depending on the gradient of that flank, it can pick up quite a bit of speed. Then if we mix water, such as rain or other forms of water, perhaps melting glaciers, things like that, into these pyroclastic flows, then they become mud flows or lahars. Lahars are incredibly destructive because they can be quite thick with the mix of the water and the volcanic debris, but it also becomes sticky and thick, and they can move up to 100 kilometers per hour, which is about 62-ish miles per hour. So easily a highway vehicle coming at you in the form of a thick gray mud. We can also get a pyroclastic density current, more commonly referred to as PDC, which is a mix of gases or volatiles that expand from starting liquid point when they're trapped in the lava coming out of the flanks of the volcano, and as they grow and expand, that can add to the violence of these pyroclastic flows or lahars / mud flows. Now, generally speaking, we are actually pretty good at avoiding all of these hazards associated with major volcanic eruptions, and that's because we have a very good system for monitoring volcanoes. And this involves primarily evaluating and keeping track of earthquake activity, because earthquakes are highly indicative of upcoming volcanic activity. When there is a sharp increase in earthquakes, both in number of earthquakes, the frequency of earthquakes, and the magnitude of those earthquakes themselves, in an area where we would normally not see that kind of activity, that could be a really strong indicator that we should be expecting a volcanic eruption from any nearby volcano. We can also look for gas emissions from fissures or cracks in the surrounding rock of a volcano. This is generally a good thing, because if gas is coming out of those cracks, that means that the pressure trapped within the volcanic channel or volcanic neck is reducing, because it's escaping out of those fissures or cracks in the subsurface leading to that channel, which means that we're going to end up with a less violent eruption. Also, changes in the local topography of the land, such as any major tilting or subsiding, can be indicative of magma flowing under the subsurface. If magma is holding up a large block of rock above it and then it moves to a different location, that rock may then fall into the space where the magma once was. So that can be a clue for us to expect a volcanic eruption relatively soon. There are a few other ways that we can monitor volcanic activity as well, and this includes, but is not limited to, deposits from past eruptions. We can see how thick the ash deposits were. That can tell us approximately how long or how violent an eruption was, what type of lava is left, hoi hoi or generally, a certain type of volcano will have one certain type of eruption, not specifically, but at least leaning on one side of the more violent or less violent spectrum. And then we can consider the history of prior eruptions on anything that we have recorded from the past. And I've got just a few short videos here for you guys that will go through, giving you a little bit better visual of how we actually go through. with these monitoring methods or how these processes actually occur.
Most earthquakes associated with young volcanoes are related to volcanic processes and may indicate that a quiet volcano is becoming active. Although large eruptions are often preceded by several significant earthquakes and many small rock-breaking quakes, there is also a continuous release of seismic energy associated with the underground movement of magma. Volcanic tremor is a seismic vibration caused by the pulsing of pressurized magma and gas. The seismogram is of longer duration and more continuous than rock-breaking earthquakes of the same amplitude. Earthquake swarms recorded by seismometers and the ground deformation monitored by tilt meters help scientists determine the depth and location of flowing magma beneath a volcano, which in turn gives scientists information to issue hazard warnings.
Monitoring volcanic gases is very exciting, especially at the very precursory phase of unrest. Primary objective in gas monitoring is to determine changes in the release of certain gases from a volcano. Such changes can be used with other monitoring information to provide eruption warnings and to improve our understanding of how volcanoes work. When the magma is very deep beneath a volcano, it has a lot of gas dissolved in it. But when that magma starts to rise towards the surface, the gases will come out of the magma. And if this happens very quickly, then the volcano might erupt explosively. At volcanoes like Mount St. Helens, it's important to monitor the gases on a routine basis because at any time there could be another injection of gas-rich magma from below, which might cause the volcano to enter another eruptive phase.
And those gases can be from either the direct top of the volcano, where it is actually venting out, or from side fissures or cracks in the side of the volcano, or bedrocks directly surrounding the volcano itself.
One of the things moving magma tends to do is it tends to deform the surface of the Earth. It tends to cause the surface to bulge upward or to spread apart. One of the instruments we use to measure deformation is a tilt meter. A tilt meter measures very subtle changes in the surface of the Earth as magma accumulates beneath the station or moves upward, for example. Another instrument we use is the Global Positioning System, or GPS. So we put several of them out on the volcano. We record signals from satellites orbiting above the Earth, and we look for movement of one of the stations with respect to the other. As the ground deforms, the volcano changes its shape, those stations move, and that tells us something about what's going on beneath the surface.
You can also have a case where an eruption is not directly from a volcano, but rather from a series of fissures from a underlying magmatic chamber. So if we look at this diagram here on the left, we have a magmatic chamber with some micro convection currents in it, and we can have some partial melting at the top that will rise due to that difference in density and come up through several lined cracks in the bedrock and flow out the surface, sort of like a sill, but rather than sitting in between two planes of bedrock, it's sitting on top of the surface. So here's another view of that, where you can see these flows piling up on top of each other. Here's the oldest flow, the middle flow, and youngest flows, all coming up through a series of fissures. And we usually end up with quite a few of these stretching a very long distance. And when this occurs, it's almost always going to be a mafic lava or basaltic rock resulting from that, which gives us what we call flood basalts. One example of a flood basalt here in the US is the Columbia River basalt. This is a map of the northwestern US. Here you can see that basalt flow actually stretches over parts, a grand part of Washington, as well as some of Oregon, a good chunk of Idaho, and a little bit into California and Nevada as well. And these are all technically part of one eruption or one flow from several different fissures, but one magmatic chamber is responsible for all of this flood basalt covering this great area of land. And that magmatic chamber specifically being a hot spot, as we have a oceanic tectonic plate to the west here subducting under our continental plate, giving us a trench at that contact. And so underneath this continental plate, right along this boundary, is that oceanic plate, which is undergoing flux melting. Recall that that is a melting that occurs at lower temperatures because of the presence of water, and is melting and rising up and surfacing right around this area and giving us the hot spot that is the Yellowstone plume. Basalt is probably one of the more fun volcanic rocks that we have, and that's because we can end up with a lot of different formations as basalt cools. On the left, we have an example of a pillow basalt. So this is similar to the Pahoehoe lava, except this happens when we have an ejection of that magma directly into the ocean. We end up with these large blobs, soft-looking blobs of hard basaltic rock on the ocean floor there. On the right, we have columnar basalt, which is actually the specific type of rock that I study for my PhD. And I love this rock, and I chose to study this rock because I think that it's fun, and it's sort of, I don't play Minecraft, but I think that it sort of looks like a whole world built for Minecraft. So there's two views of it. Here's a close-up view where you can see the roughly hexagonal shape of these columns, which fit together in a tessellation or infinitely connecting network. And these columns are usually quite long. As you can see here, there's not a good scale reference, but these are probably somewhere between 20 and 30 meters tall. And this, mind you, is in and of itself a sill. You can see that it's sitting on top of an existing bedrock with overlying sediment and rock on top of it. And felsic eruptions are those which tend to be a bit more violent because they have the higher viscosity. Recall that they have the lighter elemental composition, so they can go quite a bit further than their mafic counterpart, given the same amount of force, although the force isn't always equal. And we can have some interesting formations come out of that as well. If you take a gander at the image here on the right, we have an obsidian cliff, which is all of this black volcanic glass, as well as these conchoidal or circular patterns within that are a result of quenching or very quick cooling. Kind of like dropping a pebble into a very still lake and watching those rings expand out, except having those rings instead being frozen in time. There are also ultramafic deposits, which are much like mafic in composition, except have an even greater percentage of the heaviest elements, so magnesium and iron. They'll have at least a 70% content of those heavier elements. One common example of this is what is referred to as ophiolites. These are pieces of fresh or young oceanic plate that have been thrusted or shot up to surface by some great tectonic force at some point in time and then eroded away. On the left-hand side, you can see sort of an image of this where there is a convergence or coming together of two tectonic plates towards each other, which is sort of pinching and pushing up that underlying oceanic rock and pushing it up onto the surface so that we can see that ultramafic deposit itself, or ophiolite. On the right hand side, we can see an example of this. Mind you, our mafic rocks are darker in coloration rocks, and you can see here that this is a darker rock covered in a lighter sediment, but it isn't always exactly that color. We can have some that are a bit lighter in coloration as well. This is just depending on the presence of certain elements that have a stronger coloration effect, or any metamorphose that rock has experienced within the process of being brought up to the surface. One other very common side effect of volcanic activity is hydrothermal activity. Hydrothermal activity is any kind of geothermally heated water discharge. So anytime that we have water that has been heated to a very high temperature coming out of the subsurface at any point in time. And this can manifest in the form of a geyser. You guys have maybe heard of Old Faithful. This is a very famous geyser in the National Park of the US. That park being Yellowstone National Park, which, fun fact, is actually our nation's first national park. And while the most recent lava flow or eruption that we actually had at Yellowstone was about 70,000 years ago, we still see that it is an active hotspot because it is evidenced by the hydrothermal activity within the park, such as Old Faithful, the geyser, which still erupts from time to time. That being somewhere around 20 times a day. There's often steam or released gases associated with these hydrothermal vents and geysers. Sometimes this can have a rotten egg type smell due to the sulfur within those gases that are being released. Oftentimes they'll also be visually boiling as well, reflecting the high temperatures of around 200 degrees Fahrenheit or so. Geysers can also be seen with really vibrant colors, reds, purples, yellows, oranges, and this is because of the presence of certain bacteria that are able to live and thrive in those high heat environments, that are able to withstand those acidity and temperature conditions. Fumaroles and hot springs are also among the list of common hydrothermal activity associated with active volcanic areas. Fumaroles are giant cracks in the surface that go down to the magma chamber, where we will have a release of a mix of steam along with other volcanic gas constituents. Hot springs you've probably heard of before. There are a very wide range of hot springs in terms of temperature and size. There are some places in the US and many other countries as well where you can actually swim in hot springs, or rather pools that are sitting on top of hot springs where they are naturally warmed. There are other cases where they are far too hot for anyone to go in. I believe the closest hot spring that is swimmable to us here in Michigan would be the Palm Brook State Park that's up by Manistee. It's also known as the Big Spring or the Mirror of Heaven, but that is a swimmable spring. And that's there because we have an old volcanic ridge up in that area between Wisconsin and the Upper Peninsula of Michigan. Mud pots are also commonly associated with areas of high hydrothermal activity, and these are features in which a small amount of hydrothermally or geothermally heated water will mix with mud that is typically clay rich, and that clay will be further dissolved or fined into a thin goop by the sulfuric acid that's present in those in that hydrothermal water. And these mud pots can range greatly in terms of both size and level of pressure or violence in their boiling eruptions, but they don't often exceed several inches in length or width. Now, volcanism is actually one of the main areas where we see a strong intersect between geology and history, and this is because of the dramatic effects that volcanic eruptions can have on our society. Back in 1816, we had what was referred to as the year without summer. On April 11th of 1815, a volcano called Tambora erupted and ejected nearly 12 cubic miles of magma directly into the air in an extremely violent fashion. So the ash and sulfur in the stratospheric haze associated with that cooling and eruption of that volcano covered much of Europe and actually ended up having a worldwide effect on climate and haze or cloud coverage. And this haze blocked quite a bit of sunlight, which actually meant that we had snowfall in England and eastern Canada in June of that year. This reduced sunlight so much so that it caused several crops to fail and resulted in a widespread, in other words, worldwide famine. On the other hand, it did also cause sunsets to be really vibrant because of the way that the sunlight would reflect off of the suspended ash particles in the stratosphere. So on the right hand side we have a painting by J.M.W. Turner in 1828 reflecting the vibrancy of the sunsets during that year. Furthermore, I'm sure you all have heard of the battle at Gettysburg during the Civil War. However, it is not very well known the key role in which both the rock types and rock compositions of that battleground played in the Union's victory of that battle. The battleground is actually a deposit of extrusive igneous rocks, so these are jagged and shapely, which had since been somewhat eroded and covered by vegetation, but still left a hilly topography behind, which allowed the Union to gain higher ground. And beyond that, as they were being shot at, the hardness and resistance of those igneous rocks were able to deflect many of the bullets from the Confederates' attack. This type of bedrock also made it extremely difficult to entrench or dig out trenches in order to build fortified military arrangements to seek shelter within low ground. But because of the hardness of that rock, they were not able to dig in the same way that they would in raw soil and protect themselves, them being the Confederacy, which again helped in the Union winning this integral battle of the Civil War. So with that, few last reminders for you guys. This week we don't have too much on the table. You just have a lecture quiz to take. It's a little bit longer than the last couple ones that we've had. And that's because we had a little bit more lecture to get through. And then you have the discussion board for In the Path of the Killer Volcano, the documentary that we'll be watching during our lab time this week. So that's all for this week. I hope you guys have a good rest of your week. As always, if you have any questions, feel free to shoot me a message on Canvas or email or ask me during lab in person. And I will see you guys next time.